Good afternoon. For the first time in past 33 years, I will be lecturing in English because there are some postdocs as well as new faculty members who do not yet speak Hebrew in full command, so therefore I will speak in English. The person who would have introduced me is not here, he is abroad, so therefore I have a chance to introduce myself. My name is Itzhak Elishakoff, and I was told at MIT a story when Norbert Wiener was introduced during one of the lectures. And the person who was introducing said, "What can we say about Norbert Wiener? I have nothing to say about him because everything that I will say would be superfluous." So Norbert Wiener started his lecture and he said, "That is correct. There is nothing to introduce me because I'm the father and the mother of this topic of cybernetics. As far as I'm concerned, I'm neither father nor the mother of the topic that I will be talking about." Now, I changed slightly the title, Critical Overview of Safety Factors from Hammurabi to present. Now, the topic is almost trivial because we are teaching this topic, safety factors, in undergraduate courses on strengths of materials. And indeed, once chairman of Florida Atlantic University asked me, what are you doing nowadays? I told him that I was writing a book about safety factors. He told me, your book will be extremely short, very concise. It will contain just one phrase. Let us take safety factor equals 1.7, or you will say, let us take safety factor equals 2.3. So it turned out that my book was a bit longer than that one particular sentence. So I will present things, I hope, in a very simple manner. Now, usually when a person presents, they are talking about achievements, how nice results they were obtained. I will talk about drawbacks mostly, and then some positive aspects of the topic. And indeed, as this cartoon says, taken from the New Yorker, honesty is the best policy, but not in our company. In our company, during this lecture, we will try to stick with honesty itself. Okay. If you go to Paris Louvre Museum, then you see this stela that is called Stela of Hammurabi. That is actually exponent number 2 in Louvre Museum after Mona Lisa. This is actually a set of laws inscribed in Sumerian language, dates approximately 1750 before Common Era, and belongs to King Hammurabi. And it says, there are about more than 200 laws, but there is one law pertaining to civil engineering. And that law, there are 2 laws. One law is as follows. If the person builds a house and another person buys that house, and the buyer actually dies in an accident because this house collapses, then the builder is liable to the death penalty. Okay, this law is understandable. It is in line with eye for an eye principle that is also appearing here. You can see it in the Louvre Museum. That comes from Hammurabi's Codex. Second is less obvious. Second is as follows. If the person buys a house and house collapses and the son of the owner dies, then son of the engineer should be put to death. So you may understand that many people did not want their fathers to be engineers because if something happens, that they will be dying. But engineers were smart people. They introduced safety factors. They decided actually to build, systems with tremendous capacity of overloading and other things. So de facto, we may say that was a barbaric law. On the other hand, we can say, thank you very much, Mr. Hammurabi, because you introduced these laws, because that led actually to introduction of safety factors by the engineers of antiquity. That is this law. Okay, you may say that this law, however, looks very strong. However, even in 1804, Napoleon, there is Civil Codex of Napoleon, where he said almost the same. He did not know about Hammurabi's codex, but the codex, his codex starts the same. If a person builds a house and house collapses, then an engineer should be imprisoned for 10 years at least, because during these 10 years, they will find the cause of this collapse. Okay, I investigated the topic, who was the first who introduced actually safety factors, and found, so there are Navier, Coulomb, and others, but later I found that Bernard Belidor, in his book of this, dated 1729, introduced the safety factor, and the values that my chairman used, 2.3. He uses exactly the same number, but he does not give justification for the safety factor. He says we are using factor of security, actually. That is how French are calling it, 2.3, which means that probably some other people used that before, because he does not give any reference. That is this Belidor. Galileo also applied this concept in his dialogues. Now, but the very first time that concept of safety factor appears is in the Hebrew Bible, book number 5, Deuteronomy, Sefer Dvarim, where Moses actually instructs people that he will build the house. Okay, when you build a new house, make a parapet or guardrail around the roof so that you may not bring the guilt of bloodshed on your house if someone falls from it. Then Rambam, Maimonides, 12th century, actually postulates that this principle of guardrail should be extended to every dangerous situation. So now dangerous situation appears approximately in the 12th century. Okay, that is, for example, guardrail, and there is this distance from the top, which we call some safety margin if we want to, but sometimes the main thing is the idea of guardrail. So Rambam says, or Maimonides, that it should be instituted in swimming pools, in any other situations. For example, in France, they also use this idea. Baker's dozen is 13. Why? Because if the weight was not correct, the bakers were liable to the death penalty. So therefore, they would sell you instead of dozens, they will give you 13 breads. So that is safety factor at one times something we calculate. Okay, so every time that there is this difference, safety factors, that means that there is a theoretical difference between theory and practice, we submit, starting already from Blaise Pascal, that probably uncertainty plays a role. For example, just in a newspaper, local newspaper, lack of certainty, that article says. It does not talk about engineering, it talks about some political situation, but it talks about lack of certainty. So determinism, Michael Berry says, like the Queen of England, reigns but does not govern. So he thinks that non-determinism will be governing the behavior. So we submit that applied mechanics could be divided roughly into two parts. One is deterministic mechanics, where no uncertainty is introduced, and other is non-deterministic mechanics. Now, why do we need this? Because loads, properties, dimensions are in deterministic analysis are fixed, whereas in non-deterministic mechanics, loads and properties and their dimensions are uncertain because of the scatter of the data. Indeed, let us read how the textbooks are introducing safety factor. Okay, and I did not put the authors' names, but under deterministic approach here, external loading and structural properties are represented as though they were fully determined, and available highly sophisticated tools yield with sufficient accuracy stresses in systems with complex configuration. At the same time, these stresses are compared with the allowable ones obtained by dividing their ultimate levels by safety factor, so as to yield the level below which failure, a practice that recognizes uncertain feature of the stress distribution. Because why there should be a safety factor if we calculate stresses with extreme accuracy? This is how actually probabilistic consideration is admitted via backdoor. They do not introduce uncertainty. There is no signs of uncertainty there, but they just explain we need some safety factors because of uncertainty. Some people call it ignorance factor. Freudenthal, Professor Freudenthal, who started his career, academic career in the Technion in 30s. Okay, that is the safety factor. Sigma stress should take values less or equal than sigma allowable, which is compared with some yield stress divided by safety factor. So safety factor in actuality represents an introduction of uncertainty via the backdoor. In this sense, purely deterministic mechanics does not exist. Because if you have to introduce safety factors that you justify that is there because of uncertainty, then there is no deterministic mechanics, so to say. So this is seemingly bombastic statement. There is no such a thing as deterministic mechanics. Uncertainties are everywhere, according to Richard Feynman. Wells, H.G. Wells, statistical thinking will one day be as necessary for efficient citizenship as the ability to read and write. Indeed, now in the newspapers, every day you are confronted with various statistical data about things. And look, this is American election when they are looking whether there was a hole made during election or was no hole made during election in the year 2000. That was Al Gore thing. Very often, that is a cover page from Time magazine, mission uncertain. Usually, if mission is uncertain, then we do not talk about any uncertainty analysis. Why? Because mission is not defined. We would like to have some mission. For example, look, this is from local newspaper. That is this protection space. But a mission is to protect people. However, if the doors are remaining locked, naturally no protection can be provided by this system. That is the title of the article. It says protection, but no protection. So in this particular case, we would say that reliability equals 0. What is a reliability? Reliability is a probability that some mission will be fulfilled. Probability that there is a mission fulfillment. Okay, naturally, we will not calculate reliability in a system which is, for example, like this. We would like to calculate to have high reliabilities in the system or here. Look, I will bring you one simple example where reliability calculations were very important, and they were showed in a very simple example. This is a map of Netherlands. The hatched area is the area under the sea level. So that if Dutch would not build dikes, then this area would be flooded during floods. And it happened indeed in 1953. There was a very colossal flood, and about 1,800 people died, and damage incurred by the Dutch were at that time 2 billion Dutch guilders. In present times, it's about 200 billion Dutch euros. Then they decided to build dikes and to have some mathematical analysis of the height of the dike. And there was this rule of thumb in Netherlands. They said, if there is some dike that was breached, then new dike should be made 1 meter higher than the breached dike. In development of this rule of thumb, some Nobel Prize winners participated. Now, maybe I'll go back. However, it turned out, okay, I do a very simple analysis conducted by Van Danzig. Netherlands announced some competition, scientific competition on design of dikes. Then Van Danzig of Statistical Institute of Amsterdam presented an analysis. he used it as a problem of insurance. What is the problem of insurance? How much funds should be allocated this year in order to take into account damages which may occur in the future? So if it happens a year later, then, for example, if you put X amount of euros in the bank, next year it will accrue some percentage, so that this amount of money will grow to certain amount of money, etc. They put for 100 years. And then what are the damages? And then minimized, these damages are multiplied by probability of failure. How do they calculate probability of failure? There was one man, Wemstelfelder, started in 1890, calculate the height of the waves in one of the places, Hoek van Holland. And he came up with some statistical distribution. He spent about 50 years to collect the data. So his statistical analysis was put here in the analysis by Van Dantzig. And they calculated, and they optimized the height level. What should be the height level? Probability of failure to be minimized. And they arrived at the conclusion that elevation should be approximately 1.5 meters, not 1 meter as was taken as a rule of thumb before. That it turns out that this probabilistic analysis came more conservative than what was known before. Okay, these are the remarks on safety factors taken from various books. Second one, A, to allow for accidental overloading of the structure as well as for possible inaccuracies in the construction and possible unknown variables in the analysis of structure, a factor of safety is normally provided by choosing an allowable stress or working stress, etc. Second one, also not commonly used, this term is ratio factor of ignorance. The need for safety margin is apparent for many reasons. Stress itself is seldom uniform, materials lack the homogeneous properties, etc., etc. So there is a recognition in almost every text that uncertainty plays a role, but uncertainty is not there. There is no uncertainty introduced in analysis. But uncertainties cannot be neglected. For example, during inauguration, Queen Beatrix of the Netherlands, on April 30, 1980, she said, if one thing today is certain, that is a feeling of uncertainty. That is she. I personally think that person who introduced the safety factors was a genius. Because that actually, okay, this genius was awakened by Mr. Hammurabi, of course, and Napoleon. But on the other hand, there was some method provided, engineering method for designing structures. The question is whether something better can be done. Okay, we will consider, okay, let us go to some probabilistic analysis. We will see whether probabilistic analysis provides any input to this topic. Consider situation when the state of a structure in use can be described by some finite number of generally probabilistically dependent parameters x1, x2, etc., xn, part of which characterize the loading, and another part characterizes the strength of the materials involved. For some combination of its parameters, the system is acceptable for use, in which case it is said to be in safe state, whereas for other combinations, it is unacceptable, in which case we will say it is in the failed state. The function f of x1, x2, etc., xn, xj being possible values of the random variable xj's that capital Xj may take on, looks like this. We define it. F function should be positive. If f is positive, so we write the limit condition in such a manner that f is positive, then safe state is achieved. And if it's negative, then it is a failed state. For example, if we take this function r minus s, r is what characterizes the strength of the material, strength characteristics. It depends on x1 to x sub m. And stress is characterized by x sub m plus 1, actually, not m plus 2, until xn. And that we call margin, and that is a safety margin. Okay, then reliability of the structure. What is the reliability of the structure? Reliability of the structure in this particular case will be defined as stress levels not reaching the strength levels. Okay, strength is higher than. That means that margin should be positive. Therefore, reliability would be, if I know probability density function f sub m of small m. Now, what is a small m? Small m is a possible value of the safety margin. So it's a deterministic quantity. M, it's capital M, is a safety margin. It's a random variable. F is probability density function of this safety margin. So safety margin should be integrated from 0 to infinity. The probability of failure, however, or unreliability of the system would be P of F, will be integral of the same integrand from minus infinity to 0, where Fm of m is probability density function of the safety margin. Okay, that could be also put as formula 6 that we could calculate. That means integral from minus infinity to plus infinity, probability density of the strengths, R is strengths, and the Fs is probability density of the stress, where Fr is probability density of strengths and the other is of stress. Irrespective of the stress, irrespective of the specific densities R and S, we can also calculate poor characteristics of the probability random variables. That is mean of margin. Mean E is mathematical expectation. Mathematical expectation of strengths minus mathematical expectation of stress. Below formula 8 is variance of safety margin. Variance of safety margin equals sum of variances of R and S, respectively. Then we also can define some reliability index beta, which is mean value, because mean value has a dimension. We would like to have some non-dimensional parameter. In order to have a non-dimensional parameter, then we are introducing mean divided by sigma m, that is mean square deviation of the safety margin. And this beta turns out to be formula number 10, that is in the numerator, we have mathematical expectation of safety margin. Below there is mean square deviation of the safety margin. Now, for example, we have here also second term in the denominator, covariance of R and S. So strengths and stress may be also correlating with each other. So it turns out that reliability is given by normal cumulative distribution function of Gauss, that is defined here in formula 13, calculated at beta. Beta is a safety index. So reliability is phi function at beta, probability of failure equals phi at minus beta. And we can also calculate, maybe we don't need this. So point where D meets failure surface is called design point. So we can say that reliability actually is phi of this beta or phi of some distance from the origin of coordinate system to the failure surface. This can be easily actually shown. Now let us calculate some examples. Imagine the strengths and stress are independent and their marginal densities are exponential, that is 19. Imagine that we conducted measurements and we found formula 19, which means probability density of strengths is distributed exponentially. It depends only on one parameter, E of R. E of R is a mean strength. And then probability density is 1 divided by mean strength, exponent minus possible value small r divided by mean value. Here stress, 1 divided by mean value of stress, exponent minus stress value divided by mean stress. Reliability turns out, calculation, it turns out to be mean strength divided by mean strength plus mean stress. That is a final reliability. Another calculation, for example, can be if we know that strengths and stress are have Rayleigh distribution, that is exponent but with argument square. Then we obtain formula that reliability equals mean strength square divided by mean strength square plus mean stress square, etc. For example, in case of log normal distribution, we can also calculate results in the final form. In this case, we can actually introduce, in case of log normal distribution for both S divided by R, that is V. V is a new variable, and we would like this variable to be take values less, smaller, or equal than 1. That will be the reliability function. Now, we can introduce them, as it was done by some people. Probably first person to do this probabilistic analysis was Professor Freudenthal. Professor Freudenthal came to Israel in the 30s, started to work in the Technion, and it is very interesting that there was some strange correlation occurred between us in the sense that when I started to work in mechanics department in Technion, suddenly a person came to my office and asked me whether I wanted tea to be delivered or coffee to be delivered at 10 a.m. I was very surprised, such a capitalistic treatment, delivery of tea at 10. And he asked me, what are you doing scientifically? And I decided to explain him very easily. I got a coin, and I threw the coin, and I said, look, please, this coin can fall on head or tail, and there is this probability of 4.5, but we can imagine that airplane in turbulent atmosphere is subjected to such randomness. And this person told me, that is very interesting, but we have a faculty member who is doing stochastic control, and it would be very nice for you to get together with him. I was very surprised, and I asked myself, can you succeed in the Technion where even the person who distributes tea is such a knowledgeable person in stochastic mechanics? I told this story to Mrs. Freudenthal many years later at some conference, and she said that yes, she agrees that mean level in Israel is exponentially high. That is what she told me, or average level. Okay, we can introduce safety factor as mean strength divided by mean stress. If that is the case, if we would introduce such a safety factor or such a definition of safety factor, then first formula in an exponential case would be this coefficient C divided by 1 plus C. But in order to achieve high reliability, then safety factor C should be, say, 99, because like 99 divided 1 plus 99. Safety factor here turns out to be very big if it is exponentially distributed strength and stress. Analogous high values happen also for Rayleigh distribution. But in some cases, indeed, safety factors are demanded very high. For example, in elevator design, safety factors are about 8 to 10. So that you are doing analysis for the dimensions, and you multiply the resulting dimension by factor of 10. Because of, on one hand, responsibility, on the other hand, you don't want this failure to occur. For example, if that is a log normal distribution, also the safety factor can be put analytically calculated. Now, pay attention. Indeed, we see that if this safety factor can be justified probabilistically. That means that people who introduced safety factor, Belidor, did unbelievable achievement. They did not know that it can be justified probabilistically, but they introduced it. Leporati gives some approximate expression, for example, for this safety factor. Freudenthal himself remarks, by the way, his first paper on this topic was published in 1937 in Hebrew language. It was called Journal of Jewish Engineers. Okay, he says, it seems absurd to strive for more and more refinement of methods of stress analysis if in order to determine the dimensions of the structural elements, its results are subsequently compared with so-called working stress, derived in a rather crude manner by dividing the values of somewhat dubious material parameters obtained in conventional materials tests by still more dubious empirical numbers called safety factors. Okay, another explanation, pay attention. Freudenthal introduced defined safety factor as mean value of strength divided by mean value of stress. So that is a ratio. However, we could introduce something else, that is a mean value of this ratio, R divided by S, okay? If then we can construct such an example where, for example, R and S have uniform distribution over some interval 0 alpha, and and reliability turns out to be half, and factor of safety goes to infinity. That is what I meant. We would like to have honest explanation. Probability does not solve all problems. We are getting some paradoxical results also. Okay, so this probabilistic explanation would be, we need sigma to be smaller or equal than sigma y, or safety factor is coming here. We would like this to be far away from yield stress, and we are introducing this safety factor. We can actually construct some example, very simple example of calculating these safety factors. For example, we have an element which is subjected to some uniform stress sigma. And this uniform stress sigma has this distribution, is Weibull type distribution. Or we can also introduce something that probability density is uniformly distributed. If it is maybe I will get up because I'm connected with the table. Okay, if it is uniformly distributed, that means that probability density is a constant between lower value of stress and upper value of stress. So this is probability density is a linear function, sigma minus sigma L divided by sigma U minus sigma L. Probability distribution of sigma of stress will be probabilities that is a random stress. Everything that is random, we will denote by capital letter. Everything that is deterministic, that is possible value, we denote by small letter. So that is probability that capital sigma is not greater than small sigma. So we get this formula for probability distribution function. Sigma minus sigma lower divided by sigma upper minus sigma lower. So what is the reliability? Reliability is probability of the event that stress is not greater than yield stress. Imagine yield stress is not random, just stress is random. Then that is a probability distribution function evaluated at sigma y at this level. And just here we put sigma y minus sigma L, sigma U minus sigma L. Okay, then pay attention. Sigma lower can be calculated as average minus square root of 3, and that is mean square deviation of stress. Sigma upper is, that is symmetric expression. Mean stress plus square root of 3 mean square deviation. And then reliability look, this was what we obtained in previous formula. Sigma y minus sigma L divided by sigma upper minus sigma L. This could be recast like this formula. Sigma y minus mean stress plus square root of 3 mean square deviation, and here will be 2 times square root of 3 mean square deviation. Now we can introduce central safety factor, that is sigma y divided by E of sigma. So we divide everything by E of sigma, and then we here, instead of this term, we will obtain safety factor or central safety factor. And we obtain this one. Look, with reliability equals safety factor minus 1 plus square root of 3. That is coefficient of variation of the stress divided by 2 times square root of 3 coefficient of variation of the stress. And actually, we can find safety factor. Safety factor is 1 plus, pay attention, it's a nice formula. Safety factor is 1 plus something. You remember my chairman told me it will be 1.7 or 2.3, etc. So 1 plus 2 times square root of 3. And then this R, reliability, times coefficient of variation minus half. And that is multiplied by coefficient of variation. So it's good thing is that it's 1 plus something. Indeed, Einstein has this quote, it is incomprehensible that the nature is comprehensible. I think that we are also seeing here that suddenly safety factor can be introduced through reliability, so to say, of the system. So what one should deal with is reliability of the system rather than safety factors. And indeed, I again repeat, the person who introduced the safety factor concept was a genius. Okay, analogous results can be obtained for other cases also. But maybe we can go back. Here there are some interesting results can be obtained. Okay. If you demand reliability equals half, then actually you don't have this term and you will get safety factors equals 1. If you take safety factor equals 1, then reliability comes out in this particular case as equal half. Additional thing is that depends on the variation, how things are variable. If there is no variation, then we obtain deterministic result as a consequence. Okay, for example, in the other case of Weibull distribution, for example, if required reliability is 0.9, safety factor turns out to be 1.223. For reliability 0.99, safety factor is about 1.4. For reliability 0.999, it's 1.5, etc. So we are getting numbers we are accustomed with. Okay. So conclusion actually is, there are twofold conclusion. If you are an extremist probabilistic, then you say, give up deterministic design, deal please with reliability. If you are more mild probabilistic, you would say that reliability and safety factors can coexist together. That is, for example, the philosophy taken in Eurocode in Europe. They have both safety factors and reliabilities of the system. So concept of safety factor, which is often criticized by practitioners and researchers alike, is in actuality a powerful concept which could be given a probabilistic interpretation. Within probabilistic interpretation, safety factor is not a mysterious quantity determined by the will of the designer, for which that is a personal factor of safety. One can quantify, say, through legislation, the required reliability. And once required reliability is quantified, then one can derive associated safety factors. Okay, this is a book. It is called Safety Factors and Reliability, Friends or Foes. So we may think that we already are using uncertainty analysis via safety factors. Question is whether it can be done better. Suggested philosophy is enhancement of the existing safety factor approach. Look, please. For example, there is a system that is subject to buckling failure and stress failure. The question is, can we somehow combine this in one analysis if it is possible? For example, currently, failure mode 1 is associated with some safety factor. For example, in the problems or in articles, we see safety factor against stress overload is this. Safety factor against buckling is this. The question is, are they commensurate or not? Can we do some realignment by using reliability analysis? So at this moment, this analysis, so to say, are conducted separately. But we can combine actually, if there is some certain safety factor in one type of failure, then we would like to obtain associated reliability R1, and this, through the same reliability, we can realign the safety factors. We did one paper like this with my extremely able student Wim Verhaeghe from Belgium, who most unfortunately later died in traffic accident in Belgium. So if there are different failure modes, at this moment we have different safety factors, but they can be combined in one analysis through reliability. And here there is this example given. Reliability is a lower formula. Reliability is probability that some expression is smaller than B. At the same time as buckling failure, then this some expression is also smaller than B. And maybe we go further. We can calculate associated reliabilities, and from these reliabilities, connect this safety factor in one mode with safety factor in another mode. That works beautifully. Okay, then we go to 2. As part 2 now. Yeah, 2. Yes.
Okay.
Yes. Thank you. מה אתה אומר? משהו לא בסדר? Can something be improved maybe? No, that was a previous one. Now we go to second. Yeah, this. Yeah. Okay, on the other hand, there is something that is very interesting, that there are many people, especially in the United States, who are dealing only with probabilistic analysis. They never deal with deterministic analysis, only probabilistic analysis. I feel that overestimation of uncertainty is harmful. Why it is harmful? Because suddenly deterministic mechanism disappears from the system. They are taking some formulas from other papers and they are fetishizing, so to say, that is the law. And they are dealing with this law. Oh, it does not move. Can I press?
I think so.
Just click on the slide.
Yeah.
Okay, so can I continue?
I think so.
Okay. So what this probabilistic analysis deals actually that we could avoid by having one criterion, reliability criterion, to avoid under-design or over-design. Because in buckling, for example, we showed that structure was extremely over-designed from buckling consideration when they assigned safety factor in buckling in some problems. So we would like to avoid that. I will bring you an example of analysis where this is illustrated. Look, please. Bernoulli and Euler in approximately 1730 developed their famous beam theory. Later, Rayleigh, but even before Rayleigh, some Frenchman, Bress, introduced the effect of rotary inertia. So, for example, when there is this mass, for the concentrated mass, it is easy to see that the mass, when the beam is displacing, then this mass is also rotating. So there is this rotary inertia. But it is also in every element of the beam. So please, this Rayleigh and Bress before him in 1859, he introduced 19 years later. There is this one more term that is a force mixed derivative with respect to x 2 times and with respect to t 2 times. That is Rayleigh. It is called Rayleigh beam, or it is a Rayleigh's model of the beam. Then Timoshenko later, in 1921, but actually first, as my investigations showed, he and Ehrenfest did it together in approximately 1912. They introduced 2 additional terms. That is a force order time derivative, an additional mixed derivative in time. They took effect of shear deformation. Now it is interesting to investigate how these 2 effects are influencing the reliability. And it was done. It was done by Ehringen in a famous paper, which is in Journal of Applied Mechanics. And there they showed, look please, they showed curve below here is according to Bernoulli-Euler theory, and upper curve is according to Timoshenko-Ehrenfest beam theory. After that, no one touched this topic. Why they did not touch? Because the difference was less than 5%. So if difference is between 2 theories, less than 5%, people thought that they do not want to invest time on such problems. Then can we eliminate this line? Oh, thank you. Steve Crandall of MIT later published many papers actually on vibration of a beam that is subjected to a load at some cross-section, concentrated load. And he obtained very interesting results. He obtained results that that is a mean square velocity of the beam that is a driven cross-section, say 0.3. Now he obtained the result that also at 0.7, there is analogous result. That was his result. And there is a symmetric distribution of mean square displacement. That is by Bernoulli-Euler theory. Now, if we would have considered as Ehringen white noise is an excitation where that is a spectral density of the load is constant. But I suggested to you something that is closer to wind loading or turbulent excitation. That is that there is this constant spectral density, but within some cutoff frequency 1 and cutoff frequency 2. So we are away from the beginning of the spectrum. Therefore, because excitation is, say, from omega C1 to omega C2, the lower natural frequencies are not excited. Higher natural frequencies are excited. Because higher natural frequencies are excited, effect of shear deformation and rotary inertia become very important. Suddenly, pay attention. We have an enhancement of the response. That is Bernoulli-Euler results. These are the results based upon Timoshenko-Ehrenfest beam theory. So here it's around 0.2, here is around 0.4, and peak values are also increased very dramatically from, say, 0.35 to 0.55, etc. Actually, you can specify how much enhancement you want, and I can build the beam that will produce that enhancement. So pay attention, deterministic analysis is very important. Suddenly, effect of shear deformation and rotary inertia play a tremendous role in estimating stochastic response of the system. Can we move this? Yeah, the end is near, but it's not yet here. Then there was this publication of my paper, which you cannot read the title. It says possible limitations of probabilistic analysis in engineering. Pay attention, is also a criticism of sorts. But writing this paper took 12 years. Usually, if you want a fast promotion, you don't write such papers. What I did is I asked about 40 people, only 40 people agreed to respond about limitations of probabilistic analysis. Then I summarized this and sent to Applied Mechanics Reviews. Applied Mechanics Reviews editor declined the publication of the paper. He said that, yes, you did collect these 40 results, but you are not a secretary who collects the results. You have to summarize these results. So it took me about 2 more years to summarize these results, but I did not want to be a sole judge, so to say, of this poll. I sent to additional 10 people. So there are many, many responses. And there are many problems that probabilistic analysis has. It is very attractive, as I showed you. For example, safety factor suddenly becomes a superfluous quantity, or you can introduce it through reliability analysis, etc. For example, in probabilistic analysis, there are some assumptions that are made. For example, that is this Amazigo and Budiansky, and many papers, series of papers of that. They assume that there is this beam, nonlinear. This beam is on nonlinear elastic foundations. There is initial imperfections, and then that beam is infinite, and it is subjected to the axial law. This is a nonlinear elastic foundation, and such a system actually mimics behavior of the cylindrical shell. And they assumed that these initial imperfections are, so to say, ergodic field. And then they obtained a very interesting conclusion that stunned me, because they said this beam is, so to say, this random imperfections. So there are infinite number of beams, but all beams are buckling at the same buckling load. So I was very surprised by this result, because if it is a random system, then like when you are throwing the coin, every time there will be a different result. There will be not the same result. Naturally, people, especially in this country, of course, are not ergodic. You cannot ask what ergodic system means. Instead of considering ensemble, just consider one system, and this one system, and calculate probabilistic analysis for this one system. You cannot ask, for example, one Israeli only about his political views and conclude about the entire country. I hope that you agree that that will be not very sensible idea, and other countries also. So we decided, 2 Dutch mathematicians and myself, we decided to construct some system, Sverkogel and Kalker of Delft University of Technology. So we wanted the following system. There is some stochastic differential equations that I did not write. Then we wanted to have a closed form solution of that system, and also approximate solution based upon ergodicity assumption. Now look, that is a mean response, and that is a this is a mean response, and pay attention. Mean response we introduced some governing parameter. I wanted to have some parameter depending upon which there will be different results. So that was a design, so to say. Now we obtain the following results. If the parameter P varies between 0 to 2, then closed form solution and approximate solution are very close. At value 2, they coincide. However, that is approximate solution tends, when this P tends to 4, approximate solution tends to half, whereas exact solution tends to 2/3. That means that there is a, I hope you agree, big difference. But you may say, okay, half and 2/3, they are, from engineering point of view, maybe they are not very far. But we then had mean square value. Mean square value also behaves like this. Between 0 to 2 of these P, they are almost coinciding. Then they are diverging. Approximate solution gives 3/8. Exact solution gives infinity. That is a very big. So ergodicity assumption, or various stochastic assumptions, can have a devastating effect on your results. Ergodicity means de facto that this frog behavior is approximately ergodic. What does that mean? That where in which lilies this frog will be is determined only where it is now, not with the previous history. That is what some people maintain. Okay. Now there is another problem with probabilistic analysis. Look, Archimedes actually had said this. Give me a firm spot on which to stand and I will move the earth. That is, he meant that lever. He will put the lever there and he will be able to move the earth. That is his true statement. Analogously, probabilistic analysis say, give me the probability of density and I will calculate the reliability. There is total disregard of experiments. From this point of view, experiments are super important. You cannot just postulate experiment and then proceed with your analysis. For example, there is criticism of probabilistic methods. For example, Franz Kafka says, randomness exists only in our head, in our limited perception. I don't think that he meant probabilistic analysis of structures, but that is what he said. Israeli philosopher Yeshayahu Leibovitz said, the nature did not take the course of probability. So this gave actually to other considerations, not only to probabilistic considerations of uncertainty. So we maintain that there is something like uncertainty triangle. One is theory of probability and random processes, that is top one. Then there is fuzzy sets. So there are some people who came up with fuzzy sets. And the other people who are maintaining for some long time that we better consider things that are bounded, uncertain but bounded. That means that we should know the bounds of variation and then come up with bounds of variation of the system. This type of ideas were started to develop in the beginning of 19th century by Bertrand Russell and others. Fuzzy sets, first paper was published in 1937. Second paper, which used this term fuzzy sets, 1965 by Zadeh. Last approach was advanced in a book by Professor Ben Chaim of mechanical engineering here and myself, convex models of uncertainty, that is bounded sets. Here we were looking at that time for worst case analysis of the system. Later, I thought that worst type of analysis is very good, but maybe very conservative. Now, therefore, this English proverb says, make best out of the worst. In engineering application, optimize the anti-optimized solution or minimize the worst response derived under uncertainty constraints. In that book, we dealt only with worst type of response. Later, I added optimization of that response. Okay, look, please, fuzzy sets are also criticized. Look, Kalman, for example, says, Rudolf Kalman. I corresponded with him on numerous occasions. Falsification is kind of scientific permissiveness. It tends to result in socially appealing slogans unaccompanied by the discipline of hard scientific work and patient observation. It's a very, very big. But in some other places, maybe because of different cultures, that look, I arrived to Tokyo at some day and I saw in the local newspaper fuzzy concepts very clear in Japan. Actually, it is a bit more oxymoronic because if it is fuzzy, then it should not be clear. Is it right? It should have some resemblance of fuzziness, but they are using this fuzziness much. One can also say, someone says probability does not exist. For example, Bruno Finetti said probability is a mental construct. Analogously, fuzziness is a mental construct. What is anti-optimization? Anti-optimization is instead of looking for best solutions, we are looking for worst solutions and then minimizing that worst solution. The question is which one is right? Which analysis is right? I did not give here examples of calculation. And look, this is a fable that probably everyone heard. Then there is this judge with the stick, and two people are complaining. On the left, there is this wife of the judge, because there was no court system. He was accepting people at his home. One person complained to this sage, and the sage told him, you are right. The second person complained and made opposite comments than the first one. And the sage told him, you are right, go home. Then his wife asked the judge, how come you are telling everyone you are right? That is not possible. And he said to her, you are also right. So we actually think that all these three analyses are right. What does it mean? You can pick and choose. That is de facto some supermarket of uncertainty analysis. You can pick and choose. There will be a paper coming, our paper, we consider the same problem in three different settings. The same simple problem, probabilistic analysis, then fuzzy sets-based analysis, and unknown but bounded analysis. And we show that engineering answers are the same. So my recommendation is please, please, please introduce uncertainty in your analysis. I actually do not have a recommendation which one to use. Depends on your taste, upon your knowledge, upon your expertise, and upon your preference. Look, in our university there in Florida, once a professor came from Austria and gave a lecture. And he was asked the interesting question. If probabilistic analysis is so important, why is that everyone is not introducing it? And this person had this quote by Max Planck. The quote is as follows: a new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents finally die and a new generation grows up that is familiar with it. I totally disagree with Planck and with that Austrian person, because number of scientists is increasing exponentially, and if you want to say that I will wait till my colleagues in my department will die and they will adopt my approach, is extremely not practical. Indeed, McKay said, how can we have any new ideas or fresh outlooks when 90% of all scientists who have ever lived have still not died? Okay. You know also story by Niels Bohr and his assistant. When Niels Bohr he forgot something. He came back to his office and he saw his assistant there. And he asked him, what are you doing here? Oh, I'm working. What did you do in the morning? I was working, sir. What did you do during afternoon? I was working. When are you thinking, sir? That was a question by Niels Bohr. I think that we should also be idle from time to time and just think, doing nothing. Okay, for example, I'm teaching some course which is called Design of Homeland Safety and Security after 2001 event, and introduces all these three concepts in one course. Does anyone have any questions to my answers? That is Henry Kissinger's question, but I would like to have a discussion if you want. Thank you much. There are more transparencies, but we will leave here. Yes.
I was wondering, with the exploration of various theories, nonlinear, large and all, how your analysis fits in such theory, because the definition is not stress, is not displacement. It might be something different.
Yes.
So my question is, the approach is to go to more sophisticated tools. And I'm asking myself where it will bring us if we take your approach. Another question.
Maybe we answer first one and then we will do.
It is related
Okay,
again. It is, we are actually approaching AI. And my question is, what way AI can actually save part of the questions you're.
Okay, let us answer first question. Look, please. For example, when I did have a lecture here, I think 5 years ago before COVID, about introducing imperfection sensitivity concept in design. What we did is we compiled extensive data, measurements of shells that were conducted in Technion Aerospace Department, Braunschweig in Germany, NASA Langley Research Center. And then we had most sophisticated analytical tools of calculating buckling loads based upon initial imperfections and combined with probabilistic analysis. There is a book of mine, 2014, Resolution of 20th Century Conundrum in Elastic Stability. And that probabilistic analysis was adopted by NASA Langley Research Center, European Space Agency, and German Aerospace Development Center. So we have examples in which all three things, probabilistic analysis, experimental data, and advanced deterministic analysis can be combined in order to solve problem of knockdown factors. Knockdown factors are analogs of the safety factors. That is one thing. Let us discuss maybe this, if you have any comment on this answer. Yes, probabilistic analysis provides in many cases something that industries are adopting.
Yes, my question in regard to this, you're getting a safety factor.
Oh, safety factor
As a designer, I'm asking myself, which number should I take? If the problem, the phenomena is complex, it is not displacement, it is not stress, it is a combination of something. And as we extend the theory, then actually we can say that we can do a deterministic analysis following it, and based on this to define what would be the safety. But otherwise,
pay attention. If you can conduct deterministic analysis of something, You can also conduct probabilistic analysis of that something. Why? Because you have some criterion of failure, and that criterion of failure will be replaced by probability of failure criteria. So if you know something deterministically, surely you know you can approach this probabilistic. That is one thing. Second thing is reliability framework provides some general framework over safety factor. Reliability that you will adopt or society should adopt will determine the safety factor that you should utilize. So reliability is more generic concept, of which safety factor is a particular case. It's just one number in my big formula for reliability. From that point of view, it is not only practical, but also beautiful. It's interesting that historically, when Euler developed his buckling formula, this formula was criticized. And Euler wrote in his memoirs, my formula is not only correct, but it is also beautiful. Now, analogous thing can be said here. It is correct from the point of view that if you know probability density from the experiment, then we are getting results and we also get safety factor as a byproduct. The byproduct. I strongly advocate, to read more, if I can say that. If I can recommend, read more rather than be, so to say, skeptic. Read more because there is something already done. Things are done. Okay, let us go on to AI. So we are doing some analysis of probabilistic and non-probabilistic analysis with my Chinese counterparts, machine learning analysis, connected with probabilistic analysis. Yes, that is important, and it can reduce certain expenditures or certain efforts, and that is important, I may say. And we are excited. I did not deal here with that. More questions, please. I love actually critical comments more than the other type of comments. So I will appreciate much critical comments.
Not
Yeah.
critical, but maybe a bit of critical. So you showed the picture, I think it's 33, the slide number 33, with a table and candles in the sun, but you didn't comment it. So what is it about? Like, what was the purpose of it?
Purpose of what?
In 33.
33. Okay.
Yeah. So what is this?
Okay. Look, that is actually an item that I found in the Museum of Bouwman in Rotterdam, Netherlands. So as you see, this system is something that cannot be used in order to in your household. So assumptions very often are like this assumptions that people are making. For example, like these things are not needed in order this system to be used in order to, to deal with their T-shirt or something. So this person, he says that you are introducing this type of thing. So that is like assumption of ergodicity is like this. Ergodicity assumption makes system unusable. Very often people, extremely smart people, are introducing some assumptions that are making the theory unusable.
But what is this? Like,
Mega X. This is something irony. With it you are ironing, but now when he added these items, you cannot iron. This happened, for example, in Harvard studies that they assumed infinite shell, infinite beam, introduced ergodicity, stationarity assumption, and we are obtaining paradoxical results. What else? So you see, engineering sometimes is imitating art, we can say.
So the assumption of this infinite plate or infinite structure.
No,
ergodicity
no,
of
infinite
the-
structure is okay, but for example, to assume that it is infinite, but on top of that stationary function, randomly stationary function, contradicts experiments that we conduct. It turned out that neither, in order system to be stationary, we have to have mean to be constant, variance should be constant. Our measurements of shells in Germany, in Israel, and in the United States contradicted this assumption. So it is not stationary and therefore cannot be ergodic also, by definition. So assumptions, on the other hand, we may say as follows. Let us imagine that you would continue discussion. You would say, okay, if you don't conduct experiments, then maybe this assumption makes sense. Yes, this assumption makes sense, but when you obtain results that do not make sense, that means that every shell or beam buckle at the same level, then you should express your suspicion and then question your assumptions. If results cannot be explained physically, that means that something is maybe wrong in the system or in assumptions.
I guess you're still here, right, for today?
Okay. No, actually, I will be leaving tonight at midnight approximately, but there is an electronic mail in the first part, or you can write down elishako@fau.edu, and I'll be very happy to correspond with each of you. Whoever has any questions or especially critical comments, I would love. Many, many thanks.
Thank you.